Hey everyone, welcome back to CodeMechanic. Today we're rediving into a super common but often frustrating problem. UV got a perfectly good sensor, but the data you're getting from it is just bad. It's noisy, it's jumpy, it's all over the place. What's going on? Let's break it down. So you've hooked up your shiny new temperature sensor, or maybe an accelerometer, and you expect a nice, smooth line when you plot the data. Instead, you get something that looks like an earthquake on a Richter scale. Your first thought might be, is my sensor broken? Well, probably not. More often than not, the sensor's doing its job perfectly. The problem isn't the sensor itself, but the world around it and how we're reading its signals. Let's think about what a sensor is actually doing. It's converting a physical property like light, temperature, or motion into an electrical signal. This signal is usually a tiny voltage. The real world, however, is electrically noisy. Your phone, your laptop's power supply, the lights in your room, even motors in the nearby fan. All of these things create electromagnetic interference, or EMI. This interference is like static on a radio. It gets picked up by your sensors, wires, and messes with that tiny, delicate signal. The sensor is just reporting what it sees, noise and all. That's how a good sensor can give you what looks like bad data. Another big culprit is power supply instability. Most sensors need a steady, clean voltage to operate correctly. If your power source is fluctuating, even slightly, it can throw off the sensor's readings. Imagine trying to measure something with a ruler that keeps changing its length. You wouldn't trust those measurements, right? It's the same idea. This is especially common when you're powering your project from a USB port on a computer, or sharing a power source with a motor, which can cause big voltage dips when it starts up. Then there's the analog to digital conversion process, or a DC. Your microcontroller can't understand the smooth, analog signal from the sensor directly. It has to convert it into a digital number. This conversion isn't perfect. It has a limited resolution. Think of it like trying to draw a smooth circle using only a grid of squares. You have to approximate. This approximation process can introduce its own small errors, called quantization noise, when you're dealing with very sensitive measurements. This can become noticeable. So, we've identified the enemies: electrical noise, unstable power, and ADC limitations. How do we fight back? This is where the fun begins. For noise, one of the simplest solutions is physical. Keep your sensor wires as short as possible. The longer the wire, the more it acts like an antenna, picking up interference. You can also use shielded cables, which have a metal foil or braid around the inner wires to block out external noise. On the software side, we have some powerful tools. The most common one is averaging. Instead of taking just one reading from the sensor, you take, say, 10 readings in quick succession and average them together. This helps to smooth out the random noise, because the high and low spikes will tend to cancel each other out. This is a super simple and effective first step. If you want to get more advanced, you can use filtering algorithms. A simple low-pass filter, for example, is great for filtering out high-frequency noise while letting the slower, actual changes in your measurement pass through. It's like a bouncer at a club, only letting the low-frequency signals in. And for the really serious projects, you might look into something like a Kalman filter. It's a bit more complex, involving some math, but it's incredibly powerful. It builds a model of your system and can make very intelligent predictions to give you an amazingly clean signal, even from very noisy data. To fix power supply issues, try to give your sensor its own clean power source. Using a dedicated voltage regulator for your analog components is a great practice. Also, adding bypass capacitors close to the sensor's power pins can help smooth out any small fluctuations in the voltage supply, acting like a tiny, local reservoir of power. So, next time you see messy data, don't blame the sensor right away. Remember to think about the entire system. Check for electrical noise, stabilize your power supply, and use software filtering. By tackling these issues, you can turn that chaotic mess of data into the clean, reliable signal you were hoping for. It's all part of the journey of making things work in the real, noisy world. Thanks for watching. I hope this helps you on your next project. If you found this useful, give it a thumbs up and subscribe for more deep dives into electronics and code. Let me know in the comments what sensor problems you've run into. See you in the next one.